Hello, my friends. My name is Ming Cai. The title of my talk is Rockburst Control through Rockburst Support. This figure shows the major mining camps in Canada. Laurentian University is located in Sudbury, the nickel capital of the world. Canada is one of the world's leading mining countries, mining and selling a diversified area of minerals such as aluminum, copper, gold, etc. Potash production is ranked #1 in the world. Uranium and nickel ranked the second. There are more than 1,000 mines in Canada. Quebec, Ontario, and BC have the most metal mines. Canada has many deep mines. Lavender, Kidd Creek, and Creighton mines are in the list of the top 10 deepest mines in the world. For those who have been in Toronto, you will see the CN Tower, which is 553 meters high. You will see that from any corner in the city. However, we need 4.5 CN towers stacked together to reach to the bottom of Creighton mine. We need 5 CN towers stacked together to reach to the bottom of Lavender and Kidd Creek mine. Many mines are in the Canadian Shield, which contains some of the oldest rocks on Earth. The Canadian Shield makes up roughly 50% of Canada's land mass. In the Canadian Shield, the horizontal stress is about 1.5 to 2 times higher than the vertical stress. At a depth of 2,000 meters, the maximum principal field stress is about 60 to 80 MPa. When an excavation is created, the maximum tangential stress around the excavation can be as high as 150 to 200 MPa, which can fracture the rock easily. Due to the high horizontal stress in the Canadian Shield, mining at 3,000 meter depths in Canadian mines is equivalent to mining at 4,500 to 6,000 meter depths in South African mines from the in-situ stress perspective. In other words, our shallow mines have very challenging stress problems than many other mines in other countries. In the 1930s and 40s, mines in Ontario had been dealing with the rockburst problems in their operations. This figure shows the number of rockbursts in Ontario mines from 1933 to 1935 to 1986. A decreasing trend can be seen, which was due to improved mining method and technology. Here are a few examples of rockburst damage. Rockburst in Campbell Red Lake mine caused floor heave. A rockburst caused large rock mass bulking and fourth ground at New Brunswick mine. A 3.9 event caused extensive damage to 4 levels in Kidd Creek mine. On June 20, 1984, a 3.4 event occurred at the Falconbridge mine in Sudbury, killing 4 miners. This accident caused great concern in the Ontario mining industry. A provincial inquiry was conducted and a report produced. And this is the famous Stevenson report. One recommendation from this report was we need to conduct further research to understand the mechanism of rockburst. As a result, 3 research chairs were established in 3 Canadian universities. Recognizing the problem of rockburst, some research projects had been conducted in Canada to address the problem. One major project was started in 1985. Through this project, all Ontario metal mines started to use microseismic monitoring system in their operation. In the end, the Rockburst Handbook for Ontario Hard Rock Mine was published in 1992. Another major research project was the 5-year Canadian Rockburst Research Program, supported by 12 mining companies and the Ontario government. A major focus of this project was to add knowledge in rock mechanics and ground control. One major outcome of this project is the Canadian Rockburst Support Handbook, published in 1996. This is a landmark work that laid the foundation for rock support design in burst-prone ground. After many years of research by scholars around the world, we now have a better understanding of the conditions for a rockburst to occur. I summarize them into 4 conditions. First, mining-induced stress needs to be high to trigger rock failure. No failure, no rockburst. It's that simple. Second, the rock must have the ability to store a large amount of strain energy before failure. This is why rockbursts occur in competent rocks. Third, the rock has to be brittle. Brittle rocks tend to fail violently when the confinement is low or rock support is insufficient. Finally, the mine loading system stiffness has to be low. In this case, rock failure is unstable or violent. Rockburst damage can be in various forms. Typical rockburst damage to underground excavations include seismically induced fall of ground, which is characterized by large blocks in the piles on the floor, rock ejection, which is very common in stream burst, and excessive rock mass bulking. There are so many factors that influence rockburst damage. The severity of damage can vary greatly over a small distance in a mine because of the variability of many factors that influence rockburst damage. So we group those factors into 4 groups: geotechnical, geology, mining, and seismicity. There are many sub-items in each group. Some of those factors listed in the figure determines the intensity of static and dynamic loading, and others determine the site response. Rockburst damage is therefore governed by the combination of these factors that defines the intensity of dynamic disturbance and the vulnerability of excavation to rockburst damage. Rockburst in deep mining cannot be avoided, and we have to deal with it in mining. The question is, how? First, we need to conduct further research to better understand the mechanism of rockburst. This is our outpost. Because rockbursts are predominantly stress-driven, the first line of defense is to create favorable conditions by altering mining method and mining sequence. This is our first line of defense. We need to conduct microsystem monitoring because it allows us to reduce exposure of workers and equipment to areas of high risks. This is our second line of defense. We can do this through re-entry and exclusion policies to implement the second line of defense. Finally, we need Rockburst support. This is our last line of defense to avoid or reduce rockburst damage. In this way, we form multiple lines of defense to ensure mine safety and productivity. Rock support is the last line of defense. Therefore, it is important to build the defense line correctly. A rock support system is formed by integration of various support components such as rock bolts, mesh, shotcrete, straps, steel arches, etc. Together, they interact with each other, especially with the host rock, fulfilling the support functions. A good support system needs to have three major support functions, which are reinforcing the rock mass, strengthening it, retaining stress-fractured rock, preventing unraveling and building gabions, and holding blocks of reinforced ground in place. So effective rockburst support needs all three support functions. For the reinforce and hold functions, we need to combine stiff and yielding bolts. For the retaining functions, we need strong areal support. Stiff bolts have higher load capacity, and they do not allow rock mass to deform excessively. This is important to enhance rock mass strength, reduce rock mass bulking. When the rock mass bulking is controlled, the yielding bolts and the areal support will work better, and there is a less chance for the rock support system to disintegrate. The shadowed area in the figure indicate the energy the bolt can absorb before failure. You can see that yielding bolt has a superb energy absorption capacity compared with stiff bolt. This is why it is important to have yielding bolt in the system because of their high energy capacity. Hence, a rock support system needs to combine stiff and yielding support. They help each other, just like this Chinese saying stated, 刚柔相济，你帮我一把，我也帮你一把呀。If we ignore the principles, there will be consequence. There are a few examples here. In this figure, you will see, without any yielding support, extensive rockburst damage resulted. In this case, there's no strong aerial support, heavy rockburst damage resulted. And in this case, we don't have reinforcement support. This leads to excessive rock mass bulking. So all these damages could be avoided if we support the rock mass by properly addressing the support functions. This figure shows using two-pass rock support installation to combine stiff and yielding bolts. The stiff bolts, such as rebar, strap bar, can be installed in the first pass, and the yielding bolt can be installed in the second pass. The disadvantage of this process is that the efficiency is low. In addition, rock burst may occur before the yielding bolts are installed, which is a safety concern. To improve mine safety and productivity, we can use the one-pass system for rock bolt installation. For example, super bolts can be used for a one-pass system because super bolt has reinforce and holding functions, which is able to strengthen the rock mass and avoid rockburst damage once installed. This can create a safe, more productive working environment. There are many yielding bolts on the market right now, and it's not an easy job to select the proper bolt for your application. For rock bolt selection, we need to know the capacities of various bolts. In this figure, we plotted test data of some rock bolts. And you will see in this figure, there's a few lines drawn here. First is the OA line. This indicates the steel growth friction type of mechanism, okay? And rock bolts with this yielding mechanism will be following this line. And for line OB, this is the line for pure steel stretching for steel bar with 20 millimeter diameter. So test data will mostly follow along this line. If you have larger diameter bolts, they will be on the left of this line, OB. For other friction bolts, if it's a steel rock contact friction, there will be less than the steel growth contact friction, and the test data will be on the right of line OA. For other bolts involving yielding device, steel contact, a combination of steel stretching with friction, so all the data will be between line OB and OA. So the trend is very clear. Based on the analysis of those data, we identify that just a second. So we realized the energy absorption rate depends on the mechanism of the yielding bolt, whether it's steel stretching, steel extrusion, frictional sliding, or the combination of sliding and stretching. When you have pure steel growth or steel rock frictional sliding, the energy amount at 200 millimeter displacement is less than 10 kilojoule. For pure steel stretching, E200 could be in the range of 40 to 50 kilojoule. That's for 20 millimeter steel bar. If it's a combination of steel stretch and frictional sliding, or with some other sliding mechanism, then E200 will be in the range of 10 to 40. Another important factor to consider is the energy absorption rate. This energy absorption rate is defined as the amount of energy absorbed per 100 millimeter bolt displacement. We use E100 to represent this energy absorption rate. And you can see from this figure, rock bolts with steel stretching as the energy consumption mechanism have higher energy absorption rate than other bolts. For cable bolts made using high carbon steel, the energy absorption rate is the highest when the steel stretching is involved. For rock bolts, having frictional sliding as the energy consumption mechanism, the energy absorption rate are low. The energy absorption rate by steel rock contact friction is the lowest. For rock bolts with a yielding device as the energy absorption mechanism, they have the moderate energy absorption rate. To account for the energy capacity difference of a rock bolt tested by different direct or indirect loading, we define this energy ratio RE as ED divided by EID. So here, ED and EID are the energy capacity of the rock bolts and the direct and indirect loading. So the way that direct and indirect loading is indicated here. This is the direct loading, and this is indirect loading. Most rock bolt suppliers will test their rock bolt product using one test setup. And there was a tendency to choose the test setup, whether it's direct or indirect, that gave higher energy values to make a product more appealing to potential users. As Rockburst users, we need to have this RE ratio to make informed decision on rock bolt selection. Based on the data we collected, we presented some RE numbers in this table. You can see that for fully grouted thread bar, RE ratio is about 0.5. For fully grouted rebar, about 0.4 to 0.45. For some steel stretching bolt, the RE ratio is a little bit low. And for the hybrid bolt, this RE ratio can be in the range of 0.7 to 0.9. So this is an important parameter to consider when you have to do the rock bolt selection. And a good dynamic rock bolt, in our opinion, should have some desired characteristics. Most people think a high energy absorption capacity is all a good dynamic rock bolt should have. This is not entirely correct. A good dynamic rock bolt should have, first, high energy capacity, of course, but it also should have a suitable energy absorption rate. A larger rate is better, but this rate depends on the energy absorption mechanism, whether it's steel stretching, cold extrusion, or friction sliding. The bolt should also have a high RE ratio. That's the direct and indirect energy ratio. The best is when this ratio is close to 1. It means that they can deal with both two types of loading better. Of course, the bolt also needs to have a large displacement capacity. The bolt also should have a good barking control ability, a high shear load capacity. All those are needed for forming a good dynamic rock bolt. An effective rock support system is not just about the rock bolts. It also needs a strong aerial support. The aerial support is often the weakest link in the support system, as we see in the past. To overcome this weakest link, mesh reinforced concrete shotcrete can be used. Shotcrete is called a super mesh because it combines mesh and shotcrete. As a result, it is not only strong but also stiff, which is important for load transfer. That's to transfer the load to the rock bolts, and the bolts can do a better job if loads is transferred properly to them. Mesh reinforced shotcrete also protects the mesh from corrosion and prevent from unzipping due to individual broken wires or from inadequate mesh overlaps. Another method to use is to use high-strength mesh to build a strong area support. Most tensile strengths of the mesh use tensile strengths in the range of 400 to 600. The wire strength is only this range. But the tensile strength of the TECCO high-strength mesh is about 4 times higher at about 1,770 MPa. The use of high-strength mesh can eliminate the weakest link in the support system and provide a strong retaining system to transfer load to rock bolts and hold fractured rock in place. To enhance the area support, we can also use straps. This will make a strong connection between the bolts and the mesh or the reinforced shotcrete. Field observations and dynamic test results show that straps are effective to increase the support system's overall energy absorption capacity. Rockbolt straps are stiff, and hence the installation is a little bit difficult. On the other hand, mesh straps are flexible and easy to use. Finally, I would like to summarize the main takeaway from my talk. Rockburst risk is inevitable when mining at depths. Hence, we have to deal with rockburst, live with rockburst. There are many lines of defense, but rockburst support is the last line of defense to ensure safety and productivity. We'll get most from our investment if the support design is properly done. A good rock support system needs to provide 3 major functions: reinforce, hold, retain with good connection. Both stiff and yielding bolts are important. They are needed in a support system. They help each other to survive rockburst damage. A strong area support is critical for the support system to function. Otherwise, there will be always a weak link in the support system. For those who are interested in reading more details about Rockburst support, you can download this book free by following this link. Thank you for your attention. 谢谢大家。